Okay, so we've talked about events, sample spaces, that sort of thing, but we still haven't really addressed how we could go about calculating probabilities of events. So to that end, ta-da! So um, as it turns out, probability calculations kind of all boil down to division at the end of the day on some level. So the standard format is kind of couched in the language of set theory. So we've got cardinalities here. Cardinality of our event E divided by the cardinality of our sample space, N of E over N of S, if you will. Intuitively speaking, you may find it more straightforward instead of thinking about this in terms of the set theory language, just to think the number of ways my event can happen, the total number of possible outcomes of whatever the probability experiment happens to be. So I wanted to take a look at some of our classic examples here. So I'm going to hop over the coin flip. It's not terribly exciting. There's a 1/2 probability of either of the two things occurring. Anyway, so let's go on to talking about drawing a card out of the deck. So remember, I left the jokers in on that particular problem, and suppose we shuffle up, and we want to know how likely it is that we pull a 6 out of the deck. So in terms of our layout, well, how many different ways can we draw a 6? Well, there are 4 of them, right? So we have 4 possible ways our event occurs, divided by, in total, we have 54 total outcomes possible because of the 2 jokers. So I like to write things like this as fractions. I'd probably reduce this down to 2 over 27. For the record, if you like to write these as decimals because fractions are scary, I get that. Some folks like to represent probabilities as percentages. I'm generally okay with that as well. Be on guard, though. WebAssign sometimes wants a specific format. It will generally tell you enter a reduced fraction or enter a decimal accurate to however many decimal places. You get the idea. There'll be a percent sign in the back if they want a percentage, that kind of thing. Okay. Anyway, so now I asked how likely it is that we draw one of the hearts out of the deck. So again, assume that we've shuffled everything back in, so we still have all 54 cards available. So this time around, there are 13 different cards with a heart as far as the suit goes, divided by 54. So we can't really reduce that fraction. Again, decimals, fine, what have you. Now, conventionally, if I write something like this, that means the 6 of hearts. So it's not a 6 or a heart. I put an or in there if I wanted one or the other. We'll get to that in the next section of context. But anyway, well, provided the person with whom you're playing cards isn't cheating you, there's exactly 1 6 of hearts in the deck. So that guy is 1/54. Okay, so in the PowerPoint slides, I just used like a little smiley face icon. So face cards we conventionally refer to as the Jack, the Queen, and the King. The text talks about picture cards that lumps in the ace. I'll be honest, I've never heard that until it came up in the text, so don't stress too heavily. Anyway, we just said there are 3 face cards in each suit. So 3 times 4 gives us 12 total outcomes that are possible that are in fact a face card, divided by 54. So those are each divisible by 6, so the fraction reduces down to 2 over 9, if you like to report it that way. So the final example I've got listed in there says the probability that you draw a card with a value between 5 and 10. That can sometimes be a little bit tricky for folks. When I say between, I mean don't include those end values of 5 and 10. If I wanted you to include them, I would either say inclusive afterwards, or I'd say 5 through 10. Anyway, so that means that we want a value from 6 through 9. That's 4 values, 6, 7, 8, 9 in 4 suits. So 16 over 27. 16 over 54, and then we can reduce that fraction down because these are both even to 8 over 27. So that's card draw. While we're here, I'm going to go ahead and talk about a slight twist on this because it's something I almost always end up overlooking when I'm talking about probability calculations. So the text talks about probability. It also talks about odds. Now, Unfortunately, outside math circles, a lot of folks kind of end up using the two terms interchangeably. They'll say, what are the odds of that? And they're talking about probability or vice versa. That's not really accurate. So let me go ahead and address that real quick while I'm thinking about it, because instead I'm bad about forgetting it. It's usually like I end up tossing it in at the start of the next section. So the odds of an event so it looks a little bit different. We generally represent odds, and you might have heard people talk about 3 to 2 odds or 2 to 1 odds or something like that. So yeah, we generally look at it as a ratio with a colon between the numbers. So it would look like this. If you want to know the odds of an event happening, you have the cardinality of the event, N of E. Behind it, it's not just the cardinality of the sample space. It doesn't turn into just writing that fraction we've done for probabilities as a ratio. It really is different. We count the number of ways our event happens, the number of possible ways our event fails to happen. Remember, complements everything outside E. If you think back to what we did back in chapter 2, talking about set theory stuff. So for instance, if we wanted to look at this card drawing example. Let's say we wanted to know the odds of drawing a joker. So how many jokers are there in the deck? We said there are 2. How many cards in the deck were not jokers? Don't just list 54, because we have to take out the 2 jokers. So it would be 2 to 52, or we'll often reduce ratios like this down just for ease of reference. So 1 to 26. This isn't really wrong. It's just this is normally the way you would see it represented. You might say the odds of not drawing a joker or this thing flipped around 26 to 1. So just wanted to talk about odds real quick. We'll take a look at another one in the context of dice rolls in just a second. But all right. So we talked about probability. We talked about odds. We did some card drawing stuff. Let's roll some dice. Okay. So if you look at the PowerPoint slides, I usually couch this in the language of Monopoly, because it's a game I can be reasonably sure everybody's familiar with. So the context is you're playing in Monopoly, you've reached the late stages of the game, the property's all been bought, things are looking bad. If you land on just about anything on the board in front of you, you're going to hit something that your opponent owns, and you're bankrupt, game's over. That's bad. The good news is you've rolled doubles twice to get to this position, and if you remember the rules of Monopoly, rolling doubles 3 times in a row sends you straight to jail. So if I had more time, I'd get into my feelings about Monopoly, but I'm not going to bother right now. So the idea is no doubles, the game's over. You want to roll doubles in order to win this game of Monopoly. All right. So we want to know, in this instance, how likely it is that when we roll those 2 6-sided dice that we talked about last time, we get doubles. So for what it's worth, we've got a pair of 6s. Now, unlike most of the other examples of changing the order of these guys doesn't really change the result of the die roll. A 6 and a 6 is still a 6 and a 6 either way. So as it turns out, instead of having to worry about stuff getting doubled, we have 1 and a 1 all the way up through 6 and a 6. I can't get these rotated right. You get the idea. So we actually only have 6 possible rolls that would give us doubles. And we said last time the sample space here is 36. So our probability is just 1/6, a little less than a 17% chance if you turn that into a percentage. That's not good. It's looking bad. I'm not going to lie. So if we turn that around again, we wanted to look at the odds of the doubles. It's the number of ways it can happen. We said there are 6 rules that let it happen. On the other side are the number of ways it can't happen. So we subtract away the 6 doubles. That leaves us with 30. So 6 to 30, or if you divide both of those guys by 6, 1 to 5 odds. Again, looking pretty grim. All right. So those are sort of our basics, what you might call theoretical probabilities. I haven't actually rolled any dice or anything, or shuffled up any cards. It would end badly if I tried to shuffle cards on video. Now, the question might end up arising and kind of a bridge into my next topic for conversation. What if we don't remember the counting principle and we're trying to figure out how likely this is to happen? You start doing some sort of like mental arithmetic as you're sitting at the Monopoly table. You can see like beads of sweat, forming on your forehead as it runs down, and you're thinking about what's going on. So, what I want you to think about between here and whenever you click play on the next video is how might we try to guess how likely it is we get doubles, even if our knowledge of counting tricks fails us and we can't work out exactly how likely it is in terms of raw theory. That's what we're going to be doing next time.